Alrighty, welcome back to operating systems. So yeah, before anyone asks, the curving down or curving up or whatever, that was a joke. I didn't even scan them yet. Like I didn't even actually look at them aside from like a few. So don't worry about it. So all the exams got scanned this morning. TA is currently grading it as we speak. They'll be back to you ASAP, hopefully by Monday, something like that. I don't know. They all have their assignments. They are all currently grading. They might actually be asking me questions right now, but I'm doing a lecture. So today we get to continue our journey of file systems. So we've all used file systems before. So there's actually a usual layout we have for POSIX systems. It actually has a name. It's called the FHS, or File System Hierarchy Standard. Yes, we are very good at creative naming. Looks something like this. So at the top of your entire file system, you have a directory called root, which just begins with a slash, and that is an actual directory. And then past that, the directory has a bunch of other things in it. They're all given by names. Likely in this case, these are all represent other directories. So within root, there's a bin directory, there's a dev directory, there's an etc directory that usually has config files. Then there's like your home directory. So if you're on the UG machines, you'll have your own home directory. So in this case, it would be a subdirectory of that. Mine would be called John, and then you'd have your files in it. So like todo.txt or something like that. There's also a specified /mount, and that's where whenever you plug in USB drives or something like that, they should show up in this directory. So all of our processes, they have something called a working directory that we've probably been dealing with forever. So in this case, if my working directory is currently /home/John, so I'm in that directory, what is the relative path of todo.txt if we remember what a relative path is? So if I'm currently in the folder John, what do I have to do to get to todo.txt? Like if /todo.txt or just todo.txt because I'm already in that folder. So that's relatives directory. It's relative to wherever you are. Dot represents the current directory, and .. is one directory back. So what about to the USB folder? How do I get to the USB folder relative to John? Yeah. So relative to John, if I do .. I go up to home. Then /.. again.
Oh, sorry.
Yeah.
Yeah,
then /.. again brings us to here, and then we can go to /mount/USB. So it's a bit of a trek, but those are relative directories. So todo.txt, relative, it could be /todo.txt. Sometimes you want absolute paths. So these are all called paths. Absolute paths will begin at the root and then get you to whatever file you want. So the absolute path for todo.txt is /home/John/todo.txt. USB relative was .. to go up one, .. again to go up to the root, and then /mount/USB, or in absolute terms, it would just be /mount/USB. So any questions about that? We've kind of dealt with file systems the whole time. You'll actually see what these things represent in lab 6 and while we're talking about it. So there are special symbols here. So dot, like I said, dot represents the current directory, and .. represents the parent directory. So do we also know that, in Linux, have you noticed that when you ls and stuff, any file that starts with a dot, you can't see? It's like a hidden file. So in your Git repository, you don't see it, but there's a .git directory that holds all the information about your repository and everything like that. And in Unix or Linux or Mac OS, everything like that, if the file name or directory starts with a dot, it's like a hidden folder. Well, that was just one big mistake. So in ls, there's always a dot and a dot dot, and typically you don't want to see them. If you just do ls, it's kind of useless to see them. So you want them you just don't want them displayed if someone types ls. So a programmer was like, well, that's like two cases. That would be two if statements. That's silly. I see some commonality there. So I'll cover both these cases with a single if statement. So I'll just check the first character, and if it's the first character, if the first character is a dot, I'll assume they meant it's dot or dot dot, and I just won't show it. And that was it. And that's why anything that begins with a dot is a hidden file, because some programmer decided to be clever in like the 60s or the 70s, and that was a bug that became a feature. So, fun fact. So the other special symbol is tilde, and that usually represents the current user's home directory. It's also held in an environment variable called home. In this case, it would probably be home/John, and relative paths are calculated for the current working directory. Each process will have its own current working directory, and it will also be in this environment variable called pwd, or print working directory. So when we're accessing files, so far we've just accessed them sequentially, and we haven't talked about how to randomly access any byte in the file unless we like mmap it if we paid attention to that, which we didn't really have to, but for now, we just know how to access a file sequentially. So whenever you open a file and you do a read, well, you are advancing a position inside the file, so every time you call read, you just read more bytes from that file and you don't get any duplicated bytes, so it just keeps on going and going and going sequentially. And if you do a write, well, they're just appended to the end wherever you currently are in the file. So if you do a write system call and you write hello and then do another one that says world, well, then you'll get hello world. It'll just be appended onto the end. And the kernel has to keep track of where you need to write those bytes in the file if it represents a file. There is a way to do random access, and for random access, that means you can read and write anywhere in the file. And for that, a specific position in the file is required for each operation. So you need to say, if you're doing random access, what byte in the file do I actually want to get, read, or write? So we kind of, well, we went over the open system call before. So it just takes a path name, some flags, which can be like open it for read, write, open it for writing, open it for reading only. And there's also another flag here that is called append. So by default, when you open a file and you write to it, it just writes to the beginning. So if there was data already in the file, it would just overwrite it. So if you add a flag called append, that means that any writes you do to that file descriptor that represents the file will just go to the very end of it. So the only way to modify essentially the where in the file your read and write system calls are going to read and write from is with this lseek system call, which we haven't seen yet. So it takes a file descriptor and an offset. So an offset is just the number of bytes, either to move this pointer, so either negative, 0, 1, 2, whatever, how many bytes. And then the third parameter is whence. So whence just means what this offset is relative to. So there's a few options for this whence parameter. It's basically just like an enum in C, but it's kind of bad. So there's three options. Seek set is like an absolute offset. So that is just from the beginning of the file, no matter where the pointer currently is. So if I say whence is seek set and I set the offset to 16, that means it's going to change the position 16 bytes into the file from the beginning. If I do seek current, that's wherever I'm currently reading from. So if I set it to seek current and hit an offset of -2, it means wherever that current position is, I'm just going to go back 2 bytes. And then I can reread that same information again. And finally, the other one is seek end, so that's relative to the end of the file. So seek set is relative to the beginning of the file, seek end is relative to the end of the file. So if I want to just go to the very end of the file, I could go to seek end and an offset of 0. So it takes me right to the end of the file. So any questions about this? Yeah?
So if you do seek set and you do negative offset, will you get an error or will it loop around to the end?
So the question is, if I do a negative offset, will I get an error or will it loop around to the end? So you can do a negative, so if I do a negative offset, but I'm relative to the end of the file, that would be within the bounds of the file. It'll give you an error if you're not within bounds of the file.
So if you did a positive offset for seek end, that would give you an error?
Yeah, so if I did seek end and then a positive offset, that would probably give me an error. But if I did seek, if I had a positive offset and I went to the seek set, it would probably be within bounds unless I went over the file. But it will make sure you're within the bounds of the file. So any other questions with this? Because this makes it even more fun once we involve forking again. So forking is the bane of our existence. So here is the API for accessing a directory, which you did do in your lab. So open directory, read dir. So we're going to see how these actually work under the hood in lab 6. But here's just an example, just so we remember how we print directory content. So this open dir, well, it wasn't anything special. It actually opened a file descriptor if we straced it. And then this is how we just read everything in directory. So in lab 6, you will be making your own directories from scratch, and you will be told what file system format to actually use. So here is what is stored in the process control block. So remember, that's in the process control block, that's information about your process. So that would be the process's page tables, its threads, and its open files I just said before. So here is where we become explicit. So inside your process control block, there's going to be open files, and they're just going to be a big array. So in this case, I have the process control block for process 1, and it has 3 file descriptors, 0, 1, and 2, which are friends standard in, standard out, standard error, and they actually just point to things. So I told you before, you can think that they just point to things, so this is where we can see what they actually point to. So they will point to a structure that keeps track of the current position that this file descriptor is currently at in this file, the flags. So if I have it open for read write, write only, read only, and then this thing called a pointer to a vnode. And a vnode just represents any resource that you can actually read and write bytes from. So the full file descriptor represents a whole bunch of different things. The vnode would, in the case of a real file, point to that real file on the disk. So you can have multiple file descriptors that point to the same file that have a different internal position. So if I access it through this file descriptor, it might start accessing it from the beginning. If I access it through another file descriptor, it might start accessing it through the end. So in this case, file descriptor 0 of process control block 1 points to file A at some position with some flags. File descriptor 1 points to a different position, different flags, and a different file, in this case, file B. And in process control block 2, well, it can point to a different position independent of process 1 with its own different flags, and its vnode could also point to file B. So process 1 and process 2 could have file B open with different positions, and when they read and write to it, they have their own independent position, so they would access it serially or sequentially if they didn't do any lseeks or anything like that. So in this case, one process would not affect the other. So any questions about this? Because, yeah.
Is there a relation between this and what the function dupe did? Because I remember we also were changing the pointer in a way of file descriptors.
Yeah, so what dupe does in this case is it will take, say you do a dupe2 file descriptor 0 and say 2 and 1. What that will do is essentially make file descriptor 1 point to the same thing as file descriptor 0. So yeah, so it'll just point to the exact same thing, the exact same position, the exact same entry. Everything points to the exact same thing. So yeah, in that case, if I read from file descriptor 0 and then read like hello, and then read from file descriptor 1, well, it would keep on reading from that point. It would read like world or something like that. It'd just keep on going because they're sharing the same position. All right, any questions about that? Because it's going to get kind of weird once we start forking. Yep.
Sorry, could you explain what vnode is again?
So vnode is just a pointer to some structure that we can read and write bytes to. So it could represent a real file, a socket, a pipe, something like that. It's just called a virtual node to represent, it's virtualization. So we're just representing something we can read and write bytes to. The concrete version that we'll get into next lecture for real files and directories, there's something called an inode. And we'll see exactly what an inode looks like in the next lecture. But the super generic term that represents literally everything is just called a vnode or virtual node. Because, well, we like virtualizing things. It seems to be one of our major solutions here. So each process has its own file table in the process control block, and a file descriptor is basically just an index into that table, and that table is just a table of pointers that point to like a certain position, certain flags, and then a vnode to represent what that file descriptor actually represents. So what actually happens is when I pointed them to something, what they're pointing to are entries in a global open file table, and the kernel will maintain this, and these are all the open files across all the processes in your system. So that's how the kernel keeps track of literally every file descriptor that is open across all processes, and how it would note that, oh, does a process have the right end of the pipe open, because it would be in the big global table. So we shortened the global open file table to a GOF. Why we chose that name, I don't know. We're really terrible at naming. So the global open file table, or GOF, holds just information about like the seek position, the flags, and points to that vnode, which is just some resource that supports reads and writing bytes to. So like I said, again, we'll see what that structure actually looks like. If it's a real file, it's called an inode, and that's tomorrow. So the vnode, again, can represent lots of other things: pipes, network sockets, shared memory. What else did we go over? I think those were the main things that file descriptors represented, right? Anything else I'm missing? I don't think so. Yeah.
How big is the global open file table? Does it like get bigger as you keep opening files, or is it just big from the beginning when the kernel just starts up?
The kernel just appends entries to it, so it's dynamically resized. So it's just however big it needs to be. All right, so now we have to discuss what happens with forking with this silly thing. So remember exactly what happens during a fork. The process control block gets copied. So specifically for us, it would copy that local open file table. So just that big array of pointers that point to entries in the global open file table. So both process control blocks would point to the same global entry. So that means if they're both sharing the exact same global entry, if one process changes the position, it changes it in the other process because, well, the position is part of that global open file table. So that may or may not cause an issue. Usually it behaves how you want, but it might surprise you. So in this example, both processes point to the same global open file table. So both process 1 and process 2, their standard input file descriptor 0 points to the exact same global open entry. So if this represented like a file or something like that, well, if both processes are trying to do read system calls from that file and they're sharing the same open, global open, so say that file has 2 lines in it, well, what might happen is process 1 does a read system call. It reads the first line, which would advance the position to the end of the first line, and then process 2 could do a read system call and then get the second line. And then we're at the end of the file. Both processes would assume that that file is now empty. So we read one copy of the file because they're sharing the same global open entry, but one process gets one half and the other process gets another half. So this might happen if you're actually forking and then sharing the same file descriptors, which may or may not be what you want. So any questions about that one? Because that will probably trip you up at some point in your life. And you will have to remember this course and be like, oh, right, they're sharing the position, so the two processes, neither one of them is going to open the whole file, or you might get lucky and one process reads the entire file and the other process reads absolutely nothing. So that also might happen. So these are the gotchas. So remember the current position, that's part of the global entry, and if you fork, that gets shared between the processes. So, and also what will happen, since that position's shared, if you do that lseek system call, that changes the position. Well, guess what? Since you're sharing the same entry, if you change the position, the other process, it would also change the position in the other process because you're sharing the exact same entry. So you could fork, and then one of your processes could just set the position to the very end of the file, and the other process might not know of it, and then it would just assume that the file is just empty. So sometimes you may or may not want this. If you open the same file in both processes, that would create multiple global open file entries. So if you just call open, or however you get a file descriptor through a socket or something like that, that will create a new unique entry in the global open file table. So let's look at this example. What would happen here if, say for example, this is one process, it opens to-do.txt and then forks, and then after the fork we open b.txt, and assuming these are our only open files, how many local open files do we have in each process versus how many global open files we have, and what is their relationship? So I'll give you a few minutes with that, and then we can discuss. Yeah.
You have 3 got and 4 LLS.
Yeah, so specifically, how many would I have in each process?
Okay, so each process gets one global entry for btxt, but they will, and they will have separate local for both of them.
Yeah.
The first one, to-do.txt, they will get separate local open files, but they point to the same global.
Yeah, so each process will have 2 local open files, and in the global file table, we'll have 3 entries. So they'll be sharing to-do.txt, and they'll have their own independent b.txt. So just to go over what that looks like, so let's say we have, process, let's call it process 100. Process 100 comes open, has no files open whatsoever. Well, if it doesn't open, it would get a new file descriptor, probably file descriptor 0 if it has nothing else open. So file descriptor 0 would point to an entry in the global open file table because a new open system call creates a new entry in the global open file table. So this would have its own position, its own flags, and then some vnode pointer to a vnode that actually points to to-do.txt. And that looks ugly. So it has one entry in its local table that points to one in the global open file table. So now if we do a fork, well, we're gotten used to this. This would create a new process called 101. And since it's an exact copy of its parent, it would have the exact same local file table. So it would have file descriptor 0, which points to the exact same entry. So any questions about that? Just our good old friend fork. So now at this point, we don't know what process is going to execute next. We got process 100 and process 101. They both want to just open b.txt. So in this case, they are now independent because they are after the fork. So standard rules apply. They would each just create a new local file descriptor called 1, and they would point to a new entry in the global open file table, which would have its own position, its own flags, and its own vnode, pointer to a vnode, which would point to b.txt. And then if we went and we executed process 101, it would open its own file descriptor 1, which would point to a new entry in the global open file table with its own position, its own flags, and then, its own vnode, which points to the exact same file. So any questions about that? Yeah?
Does standard out, standard, and standard error have their entries in a global open file system?
Yeah, so standard out, standard error, they would have entries in the global open file table. And if I'm typing to my terminal, well, we saw we could do that ls of command to see what the file descriptors actually point to. So if you're using a terminal, file descriptor 0, 1, and 2 all point to a terminal. So there's a fake device that looks like a terminal that you can read and write bytes to. So whenever you do, so because you fork and then you're all sharing the terminal, that's why, since they're all sharing this position, if you type a character, so you type A and hit enter, that also means that because they're all sharing the same position, only one process is going to be able to read that A you typed. Otherwise, every grandparent would see that A as well if they read from standard in before you, and things would get weird. So that's also why the standard file descriptors work, because, well, they all point to the same position. Multiple processes won't read the same thing. Because right now, if either process reads to-do.txt, since they're sharing position, it'll advance it in both. But for both of these, they could, since they have their own unique entry pointing to b.txt, they could both read the entire contents of b.txt because they're not sharing a position. All right, any questions with that? Because it's, yep.
So are the local open files the 0 and 1 in each process? Is that what we call the LOF?
Yeah, so the local ones are just this table here. And that's what we call the LOF, or local open file table. So all they are is just pointers to some entry in the global open file table. And their index is the file descriptor you get. So the file descriptor is basically just an index into this table. So which is why it doesn't actually have to represent a file, can represent anything. So any more questions about that? All righty. So here was the answer to that. So draw nicer than my chicken scratch writing. So hopefully that is more understandable so you have it. So now we have to actually store files on an SSD or something like that. So we have to figure out a way to store these files, and how you store these files is exactly what a file system does. So remember SSDs, well, they kind of behave like memory. They have pages. So I could represent a file as just a series of pages. So how would I store information about the files? So for instance, if I have todo.txt, how would I describe where to go on that disk to actually read the contents of that file? So if you were to tell me how to use an array, what two things would you need to tell me about the array in order for me to use it? Yeah. Yeah, the start and how big it is. So in this case, if I have 3 files here, so maybe I didn't explain that well enough, so each of these files, or each of these different colors should represent a different file. So if I have contiguous allocation, if you wanted to tell me where the green file was, you could say, well, it starts at block 0, or page 0. So I'll probably use, typically when you say blocks, you talk about pages on an SSD, and it's like a file system related thing. So I'll probably say the term block, but it's just probably the same size as a page or slightly bigger. So in this case, for the green file to describe it, I would say it starts at block 0 and it's 3 long. Well, and then if I describe the red file, well, it's 0, 1, 2, 3, 4, 5, 6. So it starts at block 6, and it is 6 things long. And the blue file starts right after that, and it is 4 blocks long. So is there a problem if I do this to represent my files? So what would I have to do if I want to make the red file larger? Yeah.
You would have to move it, or you'd have to allocate backwards, I guess.
Yeah, so if I assume everything's in the same, so this is like the beginning of the file and this is the end of the file, if I allocate a block backwards, I'd have to move everything else anyways. So in this case, I'm screwed. I can't grow it because if I grow it by 1 block, since everything needs to be contiguous and all in a row, I can't grow it easily because it would interfere with the blue file, so I would have to move it and make it bigger. So is this a great idea if you are constantly making files bigger, deleting files, and everything like that? Is this a good way to store files on your file system? Probably not. We probably read and write files a lot of the time. If you have to move, so say that red file, was your 50 gigabyte Blu-ray or something like that, and well, I guess you wouldn't modify it all the time, but say it's my stream recording, it's getting bigger and bigger all the time. Well, I don't want to keep on moving it and just essentially wasting my SSD and things like that, so we need to do better with it than this. The system is going to be really fast though because, well, it's really easy to describe a file. Everything is all in a row, and you don't really need much information, so just what's starting block and the size of it. And we also have fast random access because, well, no matter where I'm trying to access in the file, since I know where it starts, and say I want to access, I don't know, byte 10,000, well, if I know where byte 0 is and they're all in a row, I just start at the beginning and go to byte 10,000, and I can know what block that byte 10,000 is at. Really easy with just one simple calculation. So it's just like the offset and block size, take the floor of that. So if my blocks are like 8 kilobytes, well, it's probably on block 1. So not on block 0, block 1. So the problem with this is files can't grow easily. So they have internal and external fragmentation. So that's a new fun term that we will also get into once we talk about memory allocation. So come up with it here. So fragmentation basically just means you are wasting space. Internal fragmentation means you are wasting space within a block. External fragmentation means you are wasting space between blocks. So I have internal fragmentation because, well, if I need an entire block for a file, and say they were 8 kilobytes, but my file is only like 10 bytes, I just write hello world or something like that, it's 12 bytes. Well, in that case, I still have to use an entire block, so most of the space is going to be wasted, and that's internal fragmentation. And then external fragmentation is, well, when I can't actually use blocks because they're not big enough. So in this case, if I made the red file bigger by 1, well, I would have a hole of 1 between the red and the blue. But if I never make a file that is only 1 block big, I can never fill that hole, and it's going to be wasted forever. So that's typically a problem once you come into memory. And yeah, this is the same problem once we get into memory allocation. So like things like malloc would also have to deal with this problem. So we can do a bit better. So everyone likes linked lists, especially based off lab whatever, what was it for? Everyone likes linked lists for some reason. So what about if we did that for file systems? So we just do a free list, like we had a free list of pages. What about to describe a file? We just link a bunch of blocks together. So in this case, if I have the green file, well, whoops. I would also save some bytes at the end of each block to point to the next block. So in this point, if my green file is 6 blocks large, well, it could start at block 0, and then the index 0 block could be this block, and then the next block could be this, next block could be this, next block could be this, and the final block could be this one. So pros and cons for this. So how do I describe what data do I need to describe my green file here? Yeah.
You need like the head, and then like each block will either point to the next page or the address of the next page.
Yeah, so if I assume that each block just has a pointer to describe this whole file, I just need to know where to start, where the head is. So that seems to be fairly space efficient, and in this case, I don't need contiguous blocks at all. One is as good as the other, so if I want to make this green file bigger, I could pick any old block and just point it to that one, right? So growing files is easy, shrinking files is easy in this case because all our blocks are the same. So any questions about that part? All right, can anyone guess what is really bad with this part? And to give you a hint, it has to do with performance. Yeah.
Because like you're always going to a different page that's not just consecutive, it slows down the performance. Also, these blocks are not always like right next to each other, so it takes time to access the next block.
Yeah, so these blocks are pretty big. Oh, yep.
Yeah, we're just gonna say it's also like if you want to go anywhere in the linked list, you have to go through all elements. So here, if you want to go somewhere in the file, you have to go through all elements. So random access, I think.
Yeah, there's a few things. So if I want to go to block 6 or block 4 or something like that, I always have to start at the head and keep on going to block 4. That's not good. I have to keep on jumping through all the pointers. And like you said, the pointers are really spread out. So one pointer is on one block, another pointer is on another block, which wouldn't be in cache, so I'd have to read it. We can assume if we're having an SSD reading each block, this is fine as any other block. They don't have to be sequential. But I still have to read every single block every single time I want to access a pointer, which would be slow. So how would I make that go slightly faster without fixing your issue? Yeah?
Use a cache, some type of cache to like figure out which blocks are used the most.
Use a cache, I could. What about if instead of, could I move where I'm storing these pointers to make them closer together? Yeah, I could just put all the pointers on its own block if I really wanted to, and just have a gigantic array of pointers, so that should speed up things a bit more. So that's a good idea, and we'll see that next. But first, this has slow random access, so space efficient to describe a file. I just need to say where the beginning of it is, and then the blocks just store a pointer to the next block. this case, the blocks would be slightly smaller, but it's probably not a big deal. Easy to grow and shrink files. We have no external fragmentation because, well, one block is as good as another. I can just point to it. We still have that internal fragmentation issue where we might not use an entire block worth of storage. But in this case, our accesses are slow because all our pointers are on individual different blocks. So, like you said, we can just put them all on a single block, put all the pointers closer together, and at least we can have slightly better performance. And in fact, this is the first actual file system we'd use. So all that array of pointers is something called the file allocation table, and essentially is that idea of just moving the list to its own block. So if you have ever heard of the term FAT32 file system or something like that, that's what it stands for, file allocation table, and it is exactly that. And if you are using a Windows computer, you are using FAT32 because your boot drive must be formatted this way because Windows told you so. So you are using this if you're using a Windows machine. So that just as the same idea, moves the pointer out of the block and then just creates a gigantic table of pointers so that everything is closer together and we get a bit of a speed up. Yep.
So will each file have its own block for pointers, or will it combine all the pointers from every file and put it into a block, I guess?
Yeah, so there'd just be a gigantic, it would just move all the pointers to just a giant array, and that array would just be a giant global array. So it's shared between them all. So you'd have to keep track of what they're pointing to and if they're actually in use or something. So in this case, using the exact same thing, in my giant array, whatever is at index 0 is the pointer of the next block to block 0. So here, block 0 points to block 6 points to block 2, and same idea as our linked list thing. So this kind of what you alluded to, this is kind of bad because, well, I need just a giant array of pointers. And how big is that array? Well, it depends on how big my disk is. So if I have a bigger disk that has more blocks, I have more elements in this global open file table. Or, sorry, why did I say that? More elements in this file allocation table. So it just gets bigger and bigger and bigger the bigger your disk is because it's essentially storing all the pointers for it. So it's pretty simple, and that's why it's used as a boot drive, like it's the file system for booting, but you don't really use it in the real world because it's kind of silly and kind of slow, and the bigger it is, the worse it is. So any questions about that one? Yeah.
So if the file allocation table is like really big, will it like use a lot of blocks, like use more than one block?
Yeah, it might use more than one block if it's that big, so, which is not that great, right? So the bigger your drive is, the bigger this file allocation table is. But that's the first one that is actually used, and you probably use it without knowing it if you're using a Windows machine. So has all the same pros and cons of that linked allocation, but it's a bit more cache friendly, so it can actually hold that table in a cache if it wanted to too, but the size of that table is going to be linear to the disk size, can become really large. So is there anything we can do here to further increase random access speed? Because, well, this still has to go through pointers and everything like a linked list. Can we do anything better? Well, let's see what we can do. Indexed allocation, just make it a big array. So instead of just having a gigantic table like a link that represents a linked list that points to blocks, I have to follow the blocks. Why don't I just have essentially a table per file that tells me which block I have to go? So in this case, for the green file could just have its own array that is as big as however many blocks it is, and then it points to exactly what block is being used. So in this case, Block 0 points to block 0 on the disk. Block 1 of the green file points to this one. Block 2 of the file points to this one. Block 3, and now I have nice random access because it's essentially a gigantic array. Well, it's an array that's as big as it needs to be to store the contents of the file. So linked lists kind of terrible. The idea here is to just use an array. So any questions about just using an array? Yeah.
Isn't this really bad if you have one massive file that consumes the whole disk?
So the question is, isn't this bad if I just have one massive file that consumes the whole disk? But if I have a massive file, I need to keep track of that number of blocks anyways, right? So what can you do? You have to keep track of it somehow. Otherwise, you can just guess, and you can't just guess. Yeah.
If each file is one block, will that mean there's a lot of different blocks for the arrays for every individual file?
Sorry?
If each file is only one block, or maybe two blocks,
Uh-huh.
does that mean there would be a lot of blocks to keep track of each file?
So in this case, so I made this red box. This is the block that stores that gigantic array. And this kind of goes back to our page tables. It kind of looks like a page table, right? Like it's pointing, instead of pointing to pages, it's pointing to blocks. So it's kind of the same idea here. So in this case, if my file is, if I have just a block that's storing all of the pointers, well, it has a limit, right? It can only store so many pointers. If your file is bigger than that, then you would need another block. Or what would you need if it was virtual memory and page tables? If I want more to address more virtual memory, what do I need to do? Add another level, yeah. So here, same idea that we'll get to later. You can add additional levels to this. So for this, oh, yep.
Or where to store for the file which block is its array?
So as part of the description for the file, here, like before we would say what block it starts at if it's like a linked list. Here we could just say what block has the array of pointers. So we could describe it by saying exactly where is the red block. So if I want to describe the green file, I'll say its array of blocks is at the red block. All right, so how big could this file be? So let's say that this index block just stores pointers to data blocks only. There's no other information. And say our disk block size is 8 kilobytes, and a pointer to a block is 4 bytes. So what is the maximum size of a file that can be represented by this index block? Yeah. 2 kilobytes? So why 2 kilobytes? Here, I'll probably have to go back and forth. So we have 8 kilobyte block, 4 byte pointers. Oops. So in this case, if we want to know how many pointers we can fit on a block, what do we need to do? Just divide them. So 8 kilobytes is 2 to the 13. 4 bytes is 2 to the 2. So we could store 2 to the 11 pointers on a single block, right? And if each of our blocks is 8 kilobytes, well, we could multiply them together to see how big our file could be. So in this case, if we multiply them together, we get 2 to the 24, or in other words, 16 megabytes. So if your file system could only support files up to 16 megabytes, would you be pleased? Some of you might be, but some of you don't watch movies, I guess, or anything remotely complicate or even have images. So in this case, probably need to do a bit better. Yep.
Well, I guess I know where the 2 to the power 13 came from, so the 8 kilobytes, but why are we multiplying it by the 2?
So we want to see how big of a file we can support. So if we use 1 block for the pointers, we can store 2 to the 11 pointers, and each of those points to a block, right? So we multiply by the block size to see how big our file could be. So that's our idea. This is file systems, more persistence, and we'll get into how to improve that later because that will do with our actual file system. So just remember, pulling for you, we're on this together.